This is Nayan, and I'm going to talk about this paper called Learning What Not to Segment, a new perspective on few-shot segmentation. This paper was accepted at CVPR 22. Few-shot segmentation has been recently successful on few-shot classification, and so most existing FSS approaches strive to achieve generalization through meta-learning frameworks. However, meta-training on the base dataset with abundant annotated samples inevitably introduces a bias towards the scene classes, thus hindering the recognition of new concepts. The motivation of the paper is to adjust the use of base datasets with abundant training samples to mitigate the bias. FSS aims for segmentation with only a few labeled data. Current approaches typically train models within the meta-learning paradigm. Given two disjoint image sets in terms of object categories, D-train and D-test, the models are expected to learn transferable knowledge on D-train with sufficient annotated samples and exhibit good generalization on D-test with scarce annotated examples. The proposed model, BAM, contains three major components. There are two complementary learners, base and meta, and an ensemble module. The two learners are used to recognize the base and novel classes. Then the ensemble module receives their coarse predictions and uses an adjustment factor psi to suppress the falsely activated regions of base classes for accurate segmentation. Here, they learn the fusion weights of different support images under the KAIST setting, aiming to provide better guidance for the query branch. This is the overall architecture of BAM. In each training episode, the two learners extract the features of input image pairs with a shared encoder and make predictions for the specific base category and the remaining base categories respectively. Then the coarse predictions are fed to the ensemble module along with an adjustment factor psi. For the experiments, the authors used two main FSS datasets, Pascal 5i and COCO 20i. For the evaluation metrics, they adopted mean intersection over union and foreground-background IOU, following the previous works. This table presents the MIOU results of different approaches on Pascal 5i. It can be found that BAM outperforms the advanced FSS models with a considerable margin and sets new state-of-the-arts under all settings. This table presents the MIOU results of different approaches on COCO 20i. Here, one-shot and five-shot results respectively surpass best competitors, demonstrating its remarkable capability of handling complex tasks. To better analyze the proposed model, the authors took several episodes during the meta-testing phase and visualized the corresponding segmentation results. Each row from top to bottom represents the support images with ground truth masks blue, query images with ground truth masks in green, baseline results in red, and BAM's results also in red. It can be found in the fourth row. The falsely activated targets of base classes are significantly suppressed than the baseline in the third row, which verify the effectiveness of the base learner and ensemble module. This figure contains segmentation results of the proposed approach on the generalized FSS setting. Note that white in the query mask represents the novel category, while the other colors represent the base categories. We can see that the bicycle in the second row here is segmented even though it is very small to check it out with our own eyes. For conclusion, the authors of this paper proposed a novel scheme to elevate the bias problem of FSS models towards scene concepts. They leveraged the base learner to identify the confusable base regions in the query images and refine the prediction of the meta learner. This way, BAM sets new state-of-the-arts on FSS benchmarks. Moreover, they extend the task to a more challenging generalized setting and produce strong baseline results. Thank you for listening.